Alright, we're in unit number 6, working through energy. In this case, this video, we're going to talk about springs, and then also Hooke's law. Springs and Hooke's law kind of go together. But before we do springs, we have to talk about a concept, a term that we use with springs. And to be able to understand springs, we've got to understand this concept. That concept is called spring constant. So let me give you the abbreviation first. With spring constant, we use the letter K as spring constant, and it is a number that describes the stiffness of a spring. For example, I've got two springs right here, and I know it's kind of tough to see on a video, but if I try to stretch this particular spring, it's kind of difficult. And if I try to stretch this one, it's very, very easy to stretch. So spring constant is a number that describes how stiff one spring is compared to another. So this one's not very stiff. I'm sorry, this one is very stiff, very hard to stretch and compress. This one's very, very easy. It's very loose. So we would say that the spring constant of the stiffer spring, this guy here, is going to be much bigger than the spring constant of this one. So when you think of spring constant, you want to think about how stiff a particular spring is. And the bigger the number, the bigger the spring constant, the more stiff, you could think of it that way, the stiffer the spring will be. Alright, so now let's go through and just basically put down what we just talked about. Each spring has its own intrinsic. Intrinsic is a word that means unique. Alright, you have what's an intrinsic DNA. No one else has one like that. That would make you unique. You are intrinsic. Unique and intrinsic mean the same thing. Each spring has its own intrinsic, unique K, spring constant. And in the lab, actually, we're going to actually calculate the spring constant of a given spring. The spring constant of a spring remains relatively constant as long as the spring is not stretched beyond its normal elasticity. So back to these two guys. Let's say the spring constant of this is 5. We'll worry about the units in just a bit. It's 5 whether it's here, it's 5 whether it's here, it's 5 whether... Now, if I just completely stretch it beyond its normal elasticity, then obviously the spring constant is going to change. But generally, the spring constant is going to stay the same regardless of how far you stretch it. Same thing with this one. Doesn't matter how far you stretch it, it'll stay the same. And then, like we said earlier, the greater K, the stiffer the spring, and the smaller the K, the looser, and I think I've got that spelled right, the looser the spring. Okay, the next page. All right, here's Hooke's law. When we talk about Hooke's law, we're going to have in Hooke's law, it's an equation. And Hooke's law in that equation has a variable, it's x. You need to know what that x is to be able to use Hooke's law. So before I give you Hooke's law, I'm going to show you what x means or how to determine what x is. So I've got 3 pictures up here, and I'm going to work you through each picture and show you how you determine x. X is a distance. And x is always determined, or always drawn, or always measured from the equilibrium. We'll talk about equilibrium in just a moment. From the equilibrium to wherever the object is at. So for example, I've got a mass on a spring. This is in physics. This is what we use all the time. So this is like a wall right here, and that wall has a spring hooked to it, and then that spring is stretched over to this particular object. Now, if I let go of this object right here, it would oscillate back and forth about this equilibrium. If I were to let it go long enough and there was some friction involved, it would eventually come to rest, and it would come to rest right at its equilibrium. So the equilibrium is more or less its resting point. It would be where it would be if there was no force acting on it. Alright, but in this case there is a force acting on it, so we'll put the object out here. So the x is always a distance, and it's going to be measured from the equilibrium. So you put your pencil on the equilibrium and just draw an arrow all the way out to that object. And then that is x. X is going to be a vector because direction is important. So I'll put a vector arrow right on top of it. So if this was 5 centimeters, then I would say 5 centimeters. In this case, it's to the right, so it would be positive. Okay, here's another one, part B. So here's the wall. Here's a spring attached to the wall, a spring attached to the box, and here's the equilibrium down here. So it's always drawn, remember the x, the displacement is always drawn from the equilibrium to the object. And there it is, and that'll be x. So if that was 10 meters, that would be like positive 10 meters. Here's the next one. Here's the equilibrium, always drawn from the equilibrium to the box. And so that would be x right there. And in this case, it would be, let's say it was negative 20. So negative 20 meters. Negative because they're going to the left. So it's always drawn from the equilibrium. From the equilibrium. And I gotta sneeze here, so let me turn the mute on. Alright, I think it's out of me. Alright, so we're going to work through a demonstration. And so here's the demonstration right here. It's kind of tough for me to set this up on a video, but I'm going to do my best job. I have what is called a spring scale right here. Let me back out of this a little bit. That's about as best I can do. Maybe I can tilt this up. There we go. Alright, so I have a spring scale. And on that spring scale, let's say this. Inside that spring scale is a spring. And the goal of this little demonstration is to determine the spring constant of that spring. And to do that, what we're going to do is this. We're going to take a mass right here. I can't do this on a video because in the video it's horizontal. But what I'm going to do is I'm going to literally hang the mass like this. And then I'm going to get the reading right off of the scale. All right. So before I do that, I'm going to go ahead and draw a diagram of this on the notes, and then I'll come back and I'll show you what I'll be reading off the scale. So let me first zoom in a little bit. And we're going to basically use a free body diagram to determine this first. So here's the mass. All right, and we want to know the forces that are acting on that mass. So what forces are acting on it? Well, there's gravity acting on it. Gravity's pulling it down. We would call that the weight of the object, or Fg, the weight, the force of gravity. And then there's also a spring pulling it up. And so we're going to use Hooke's law to figure that out, and I'll show you Hooke's law in just a moment. So those are the forces that are acting on the spring. Spring's pulling up, weight's pulling down. Here it is down here. So spring is pulling up right here. Okay, it's pulling up, and then gravity is pulling down. Maybe I can do it in the orientation that's shown here. So spring is up and gravity's down. All right, so since we have a free body diagram, you know from previous chapters that we're going to use Newton's second law to go ahead and analyze this. So there it is, and we're doing y direction, so there's Newton's second law. What forces do I have acting in the y direction? Well, I have the spring, and I have the weight. It's at rest when I'm hanging it, so if I were to hang it just like this, it would be basically at rest. So there's no acceleration. So I'm going to go ahead and solve for Fs, and there it is. Now, my goal is to figure out the spring constant. So to do that, I need to give you Hooke's law. So I'm going to scooch over, and on the side over here, give you Hooke's law. Hooke's law is F equals negative Ks. This is the force exerted by a spring. So a lot of people just put it, I've seen some people put an S right in there, but you don't have to do that. All right, so let's go through each of these variables and justify the units and make sure we understand this. I'll do the X at the end. So let's start with the K. K is spring constant. We talked about that already. And I'll work you through the units in just a moment. X is what we talked about up above. X is the distance from the equilibrium. The negative indicates that the force and the X are always going to be opposite. Let me come back over here and show you what I mean by that. I'm looking for another pencil besides, or looking for another color besides this one. And we'll use use red. All right, so notice that when the object is out here, the x, which is a vector, is to the right. Now notice which way is the spring pulling on the box. The spring is pulling on the box in this direction. So this is the force of the spring. Notice that those are always opposite one another. Let's go to this one real quick. The spring is pulling up on the box. I lied. The spring in this case is going to be pushing down on the box because it's past its equilibrium, so the spring is trying to push it back towards its equilibrium, which is going to be an important concept in just a bit. Notice that they're opposites. And over here, the spring is pushing in this direction, past its equilibrium, so it's trying to push it back to equilibrium. Notice that those are always opposite. So if this were plus, the x would be minus. If this were minus, the x would be plus. If the force were minus, the x is going to be positive. And to account for the fact that when one is plus and the other is minus, to make it work in an equation, I always have to have that negative there. So that's why the x is there. All right, let's use the equation now to determine the units for spring constants. So I'm going to go ahead and solve the equation for k, which gives us negative f over x. And then I don't have to worry about the negative when I'm doing units. So this is going to be newtons divided by meters. And that's the unit for spring constant. So when we talk about the spring constant of a particular spring, we're talking about newtons per meters. We don't have a special name for newtons per meters. It's just newtons per meter. And in my opinion, on the test, when we go through units on the test, most students, if they're going to struggle on units, they're going to struggle on spring constants, the one that they typically forget or get mixed up with some other unit. So remember, spring constant is newtons per meters. So just to take this one step further, so if I had two springs, and one spring was 2 newtons per meter, and the other spring was 5 newtons per meter, which spring would be stiffer? The 2 newtons per meter or the 5 newtons per meter? Well, look at what it says. This says it takes 2 newtons to stretch it 1 meter. This spring constant says it takes 5 newtons to stretch it 1 meter. Well, then this is going to be stiffer than this one. So the higher the spring constant, the stiffer that particular spring is. Since we're on that concept, let's just jump down. I'll come back to the example in just a moment. Let's jump down and do these 2 bullet points. A spring constant of 2 newtons per meter means that it requires 2 newtons of force to stretch it 1 meter, or, well, let's see now. How much is it going to take to stretch a half meter? Well, if it takes 2 newtons to stretch it 1 meter, it'll take it 1 newton to stretch it a half a meter. All right, moving on. Record spring constant, that'll be K, on your dimensions and unit sheet. Include the most common unit. The most common unit is going to be newtons over meters. A secondary unit would be like pounds over foot. We don't usually use that, but it's there. And then the governing equation is going to be F equals negative kx, and that's going to be Hooke's law. So I would stop the video real quick, include that on the unit sheet, your yellow sheet, and then come back and finish out the video. So let's come back up here and finish this out. Since I now have an equation for F, which is going to be negative kx, and then that's going to equal W, but we know that W is equal to mg, then I can go ahead and take that equation and solve for k. So k then is equal to mg over negative x, and then I can plug in all the numbers. So m is the mass that I have on the scale, and the mass I have on the scale, and I'm going to go ahead and show you basically what that is. So if I hold the scale, you can't see this real well, but if I hold the scale, let's see if I can do this and not change it much. You can kind of see that. It's right at about 600 right here. Maybe a little shy, maybe about 580 or so. So I'm going to go ahead and put that down. So 580 grams, so I have to convert that to kilograms. So that's going to be 0.58 kilograms times 9.8, and then all divided by the distance that it stretches. Now this one's going to be a little more difficult to determine, but I'll show you how we'll actually do that. Looking for a ruler. So when there's no mass on the spring, then the marker that I use to determine the weight of the spring, or the mass of the weight of the object, or the mass of the object, is this brown little piece right in here. And as it is dragged down, then it stretches the spring. You can kind of see it as I do that. So that would be at 0 point. And then what I'm going to do is I'm going to go ahead and stretch it down to, what did I say, 580? So 580 is right here. So what I'm going to be doing is, see if I can do this with only 2 hands. I need to know the distance from here, which is where it started, all the way down to here. And that would be, well, this example is not good, but if I were to stretch it down here, it would be this distance here. That's my x, because the equilibrium is right here. This is when it's just plain old resting. Okay, when it's resting and nothing's happening, its equilibrium is right here. And then I'm going to go ahead and measure down. So take my ruler, turn like this so you can read the ruler with me. And get on the metric side. So I said 580. So here's the 0, and 580 is about right here. So that's going to be about 3.4 centimeters, and that'll be the x. So let me come back over here, grab this. I said 3.4 centimeters, which is going to be 0.0. Yeah, 2 spots. 0.0034 centimeters. Is that right? 1, 2, 3. No, I have to put 1 0 in there actually. So when I convert, so 1, 2, yeah, there it is. So that'll be the same thing as 0.034 centimeters. So if I've confused you, let me try it again real quick. So 3.4 was the distance that we measured. Then if I want to convert it to meters, I move it over 2, so 0.034 meters. All right, which is what I have down here. And then I'm going to go ahead and just plug the numbers into my calculator and get the final answer. And that'll be the spring constant of this particular spring. So 0.58 times 9.8 divided by 0.034, and then get the answer. So 167. I'm running out of room here. Let me erase a little bit of what I have here. So 167, and that'll be newtons over meters. Now, some of you may have noticed that I made a mistake. Did I make a mistake? Where's it at here? Ah, here it is. All right, so I have the negative in here, and you're like, well, where did the negative go? Should it be negative? Well, let's just see what's going on here. If I go back to my concepts, spring constant should be positive. It's going to be positive every time. And if you look at just the math on this, the math is showing that I only have one negative, so that negative is going to show up right over here. And I can't have a negative spring constant, so I've got a mistake someplace. So the question is, where did I lose my negative at? Well, nothing was lost here because the spring force was up, the weight was down, so that's why this is negative. When I shifted around, these two are positive. When I substituted, a negative showed up here, and that's because of Hooke's law is negative kx. When I solve for k, I get mg over negative x. So no mistakes there, but I need to include the negative right here with 9.8. And so that'll show that negative divided by negative will give me a positive 167 newtons per meters. And there it is. All right, let's do the key concepts down below for Hooke's law, and we'll wrap this video up. Pull this out just a little bit so we can read the whole thing. All right, the F in Hooke's law is a restoring force. All right, what does that mean, a restoring force? Well, if we go back up to our diagrams, notice that these forces are always trying to push it back towards equilibrium. The force is always trying to push it back towards equilibrium. Over here, it's always trying to restore it back to the equilibrium. So We call that, when it tries to restore it back to the equilibrium, restoring force. The force needed to return the spring to its equilibrium point, or its relaxed length. X represents the displacement of the spring that is stretched or compressed from its equilibrium point or its relaxed length. X is a vector. We talked about that earlier. And its sign, so its direction and its sign is important. And that's valuable. And I made a mistake. I got to go back up and fix it. All right, the negative indicates that the restoring force, F, and the displacement act in opposite directions. Okay, let me go back up and fix a mistake I just registered in my head. Hey, remember when we talked about Newton's law, Newton's second law? When we use Newton's second law, if we determine the signs up here, so we said that weight is negative up here, we can't later on use negative for the 9.8. So that was my mistake when I did this. So you either use the negative here or you use it here. And since I used it up at the top, I can't use it down here. So this is really positive. But let me show you where the negative does pop up that we couldn't find earlier. Notice that on this particular diagram, the equilibrium was going to be, oops, you can't see that. The equilibrium was going to be up here. So we actually displace, when you put a mass on a spring, you displace it below its equilibrium. So that distance that we had, or that displacement right here, is always going to be negative. So there's a negative that comes over from the equation, and then I should put actually another negative in here, which does make this positive. So I did have a mistake, but I got it fixed. All right, that's this video. On the next video, we'll take a look at spring potential energy.